What's your understanding there? So what do we mean when we say that parallel planes have the same Miller indices? We mean this plane here, that one, and that one are parallel, isn't it? At no place will these two, for example, planes meet. Huh? It means that the distance in between them is maintained, okay, to infinity. Same as these ones. So you have that plane over there and this plane over there. The distance in between them is maintained throughout, okay? So the distance between them is constant to infinity also, same as these two here. So these three planes are referred to as similar ones, why, or equivalent planes, because they have similar indices, and at no point do these planes ever meet. Same as these ones here. Okay, so we'll just learn how to draw planes in our next slide. So let's try this exercise. Let's try and see how we come up with these planes. So the plane in blue, this one is the 110 plane. So if you remember, when we're looking at directions, there's a difference between directions and planes, vector directions. There's a difference there. So what this means is, recall what we did last time. Let's try and recall together. Let's try and draw a direction. Let's go back to our previous lesson. So for direction, if it was 110, we're going to come 1 here, right? And then go 1 there. Okay, then 0, don't go above. So meaning our point would be here. Then when we connect our 0 to this point, that would be our direction. Okay, however, for planes, it's different. So with planes, what you do is, when you have 110, for example, 1 across X means you mark a point there. Okay, and then 1 on Y, you mark a point on the Y axis. Okay, and then 0, Z is 0. It means that you're not marking anything on the Z axis. In short, it means that your plane is parallel to the Z axis. So you have those 2 points, you raise them like that, okay, and there you have your 110 plane. Okay, as you can see, this 110 plane is not touching the Z axis at any point. Why? Because Z in this case is equal to 0. Therefore, it does not touch the Z axis at any point. If anything, this plane is parallel to the Z axis. Let's try this one below here. This is a 100 plane. Actually, it's not 110. This is a half 00 plane. Okay, so you have, so it's a half 00, or as we like to say, infinity, infinity. So 1 halfway there, okay? Along the x-axis, you move halfway. Okay, so B would be 0, or infinity in this case, huh? So what does infinity? So the 0 means infinity, like I said, isn't it? If they're parallel lines, then their distance is maintained to infinity. Okay, that's why we have the infinity sign there. So same here. If the B is 0, what does it mean? Or infinity? It means that this particular plane that we're trying to construct is parallel to the y-axis. Okay, and then also look at C direction, which is, sorry, when you look at the C distance, which is in the Z direction, it is also 0, meaning it is also parallel to the Z direction. So what do we have in 10? We just had that point there, isn't it? So we just extend that line there, upwards, over there, and down. And there we have our half 00 plane. So when we convert that to indices, remember we said with indices, we do not have integers. Okay, we use the same issue that we used last time to say we need to find reciprocals and then reduce, and then we come up with our index there. Okay, so what's the reciprocal of half? It's 1/2. infinity, 1 over infinity, 1 over infinity. So 1 over infinity mathematically is equal to 0. Okay, so you have your zeros there. 1 divided by half gives you 2. So you have 2, 0, 0. Reduce 2, 0, 0. And then you should have, so the 2, 0, 0 plane, remember we said that the planes that are similar, 2, 0, 0 is the same as 1, 1, 0, as 1, 0, 0, sorry. Okay, these planes are parallel to each other. 2, 0, 0 means this is 1. Okay, then 2 will be in the next lattice. Okay, the lattice that is in front of this one. So forward there, that's where the 2 would be. So you would similarly draw a plane just like this one. And what you discover is that it will be parallel to this plane here, the half 0, 0 that we've drawn. Okay, so these are basically similar planes. So just to depict into what we have already, it means 1, 1, 0 is this one. So same as this one, if you have the 1, 1, 0, meaning you come here once, okay, y is infinity, z is infinity. So you have that over there. Okay, the face of the lattice becomes the plane of interest, the 1, 0, 0 plane. And obviously you see that this plane here, the face, the front face of this lattice is actually parallel to that half 0, 0 plane that we drew initially. Any questions? Okay, let's come to the one more. Maybe then we invite questions. Let's try this one. So this one is half 1 and 3 over 4 plane. So how do we draw the half 1, 3 over 4? Very easy. Same tactic. Nothing is changing with the planes. So along A, we come halfway. Okay, that's halfway. And then B is 1, isn't it? So meaning on the y-axis, we're coming all the way 1 unit, which is at the end of the lattice. Okay. And then C is where 3/4 the distance. So 3 over 4 is marked over there. So you have 3 points, this point, that point, and that point. Then you simply join them together and there you have your plane. So now in terms of Miller indices, how do you convert these intercepts? Same formula, get the inverses, okay? 1 over half, 1 over 1, 1 over 3 over 4. When you do that division, what do you get? You have 2, you have 1, and 4 over 3. Okay. Then from here, you need to find a value such that it will help you rid of this fraction, 4 over 3. So what value is that? What value are we going to use to multiply by all these 3 to help us get rid of this fraction? Anyone? Tell us what number we multiply here.
3.
3, exactly. 3. So this means that when we multiply, so 4 over 3 multiplied by 3 gives us what? The 3's will cancel, and then we'll have 4 over 1, which is the same as 4. Okay? 3 times 1 is 3. 3 times 2 is 6. So there we have it. These are the lowest common ones. What do you used to call these? Common factors. So you cannot reduce them any further. So that's what we end up with. We end up with 6, we end up with 3, we end up with 4. Okay, those are the Miller indices. So a question can come in such a way, find the Miller indices for the following intercepts, half, 1, 3 over 4. Draw the plane, maybe to ask you, maybe the question will ask you to require you to draw the plane also. So there you have it. Okay, so like I said, the family of planes is the HKL, okay, H being the x-axis value, K being the y-axis value, and L being the z-axis value. So this is an example of the different types of planes that we can actually draw for ourselves. You can try and practice these in your own time, but for now, let's have questions.
Madam, kindly repeat. I was on my way back home. I've just reached. I couldn't get anything
Okay.
in the car.
Okay. So what do you want me to repeat?
For example, maybe on the same, any of the examples, one of them.
Okay, let me get the easiest. Let's start with the first one we did, the 110 plane, or the 1, infinity 110. So like I said earlier, okay, let's try and draw it together. So 1, okay, unlike the directions were actually following the points like that, isn't it? Going wherever they went. But with the planes, we're just simply plotting on the axes themselves. So in the case of X, we have 1, okay? So 1 unit per, mark it there, okay? Y, 1 unit also. So from 0, you go 1 unit in the Y direction. It's a positive 1, so you come there, mark it. 0, okay? This means that this plane is parallel to the Z direction. That's what the 0 means. If the 0 was here, it was going to mean that the plane is parallel to the X direction. If the 0 was on B, it was going to mean that the plane is parallel to the Y direction. Okay. So in this case, the plane is parallel to the Z direction. So meaning at no point does this plane meet with or cross the Z axis. Okay, whether plus or minus, that's what it means. So it means the distance between them is maintained to infinity. Okay, that's why we have an infinity sign there. So in this case, we plotted the 1 there, we plotted the other one there. So what we simply do to complete the plane is we just raise those lines like that and then join them to the top. Okay, then we have that cutting across. Okay, it's almost as if you got a knife and you attempted to cut your cube in the diagonal. Okay, that's the plane that we've achieved. That's the 110 plane. So in terms of indices, how do we get there? With the intercepts 110 or 1 infinity. So we replace the 0 with infinity. Then we get the reciprocals, okay, of all these values, which should be 1/1, 1/1, and 1/infinity. Mathematically, 1/infinity gives you 0. 1/1 gives you 1. 1/1 also gives you 1 here. So you have 1, 1, 0. Indices, no commas in between them. There you have your indices. Okay, I hope this was enough for you. So in the case of half infinity, meaning across the x-axis, we came halfway. Okay. B, it's infinity, meaning along the y-axis, our plane is actually supposed to be parallel to the y-axis. And also because Z there, our C is 0, it means that C is supposed to be parallel to the Z-axis. So what we have instead is what we pick there, which is halfway through the x-axis. And that is our half infinity. Then as well, we convert this to indices, we'll get 1, 0, 0 using the same procedure. Okay, so we'll move forward. Okay, here's an example here also. Let's try this. Determine the Miller indices for the plane shown in the sketch. So I hope you see the sketch there. That's a 0, 1, 2 plane. So let's try and see how this sketch came about. 0, -1, then 2. So meaning in this case, because of negative value, you can actually move the axis, okay, up to here. So it was moved, in short, the 0 here was moved and replaced here. That's one thing to note. What else is worth noting here? Okay, let's begin the plotting. So 0, what does 0 mean? It means that we're not moving in the x direction, isn't it? And then what does -1 mean? Where are we going? Where is -1 on the y-axis? This is the y-axis, isn't it? A negative value initially should be this side, yes?
Yes, madam.
You have a question?
No. I'm just
Okay, all right. Oh, okay.
uh,
So it should be on
agreeing
this
with you,
side,
yes.
isn't it? But then when you move the axis and place it here, it means that this becomes your negative. Okay, so meaning when you move that way, you'll be moving in the negative, in the case where you've moved your axis. Okay. Why are we moving it? Because of the 2 also. The 2 will require us to move now into it's a different lattice also for Z. Okay. So the movement also adjustment along Z and adjustment along Y. Okay, now let's forget about adjustments. Let's say there were no adjustments. How are we going to have our plane? How is our plane going to look like? Okay, so along X there, it's supposed to be parallel to X, isn't it? There's supposed to be like an infinity distance between them. And then along Y, you have -1. So -1 would have gone this side, right? So we'll go 1 unit in the next lattice. And then mark our 1 unit, -1 unit on the y-axis. And then Z requires us to do what? To have 2. So what does 2 mean? It means that we're supposed to go not in this, 2 is not in our current unit, okay, at this plane. 2 means that it's in the other plane, okay, over there. So it was supposed to end somewhere there in the next, so in the line of the cubes that are above this one, the lattices that are above our current one, okay, so there's supposed to be another unit there, isn't it? And there'll be another one there. Then where this one, the one on top where it's ending, the top of it, the top base of it, that's where we'll have our Z coming in. So it will be a bit complex for us. That's why in such cases, we have to move the axis, okay, just for us to facilitate those movements, because it would be very hard for us to actually draw one that is coming from different lattices like that. So how do we come up here? So let's try and use these values instead. So what values are we given? The intercept, you have, what do you have here? You have infinity multiplied by A, okay? Then you have -b, and then you have C/2. Okay, so those are the intercepts that we use. Those are the ones that we're going to use to draw our plane. Okay, so infinity multiplied by value gives you what? So you have A distance multiplied by infinity, that's on the x-axis. So that's 0, isn't it? Then Y is -b. So instead of us going in that direction, we move the axis and bring it here, okay, provisionally. So meaning would have moved by a step over there. Then half means what? Halfway the Z axis will come over there. So we'll have that line like that, over that becomes our plane. So now how do we bring it to indices, the 0, 1, 2? That's we all agree that is a bit, it would be hard for us to draw up. But however, the intercepts are what would actually use to that's what we've been using to determine the plane. So you have our infinity at x, okay, when you multiply that, -b, b being 1, right? That would be -1. C/2, c being 1, we'll have half. Find the reciprocals and then get rid of the fractions. You have 0, -1, and 2. Then that's how you write it like that. The overbar is on 1, okay, because it's a negative value. So you have 0, 1, and you have your 2 over there. So also with this, also what is known as the interplanar spacings. Okay, so this is basically the distance between are the atoms, okay, that are in our lattices. Okay, they are obviously arranged in a certain manner. And the idea here is that if the rays that came, okay, and bounced on your crystal, how would they bounce back? Okay, there's an angle that will form, a theta angle that will form. There'll be a distance d, okay, there'll be that angle there, okay, of the reflection. That is that you're also going to determine. D is the distance between those planes, between the planes. Okay, that is our D. And how do we find this D? D is equal to A, yes, I'm recording. D is equal to, this is a formula, A over square root of H squared plus K squared plus L squared. Okay, so H, K, and L are Miller indices of the plane. Okay, so if our indices were, like we had initially, we had what, 0, 1, 0, negative 1, and 2. So H would be 0, would replace H with 0. Here we'll have negative 1, and then here would have 2. Then A would be given, that's a lattice constant that will be usually given, okay? If A is not given, sometimes you'll be given R. Radius will be given of the atoms. So we already know how to figure A is the distance that you have there, actually the distance of the lattice itself, the lattice cube of the unit cell. So you know how to find R when you, how to solve for R or how to solve for A. So in the case where you're given R, you use those formulas. Remember for FCC, we had a particular formula that we're using to find our A, to determine our A. So you simply, if you've been given R, you put the R there, R value, the radius value, and you find your A, which you come and place here. Okay, so these values you'll be given. If it's 1, 1, 0, you'll be given. If it's 3, 2, 1, and so on, you'll be given. Okay, so the wavelengths of the X radiation are the same magnitude as the interplanar spacing in the crystal. I think I think I'll leave you to actually read this for yourselves. Let me see if we have an exercise here on the same. So you'll find this in the recommended literature, the one I shared with you. You'll find this also in your modules. You read in depth just to understand exactly what is going on. So the condition for reflection is given by Bragg equation. So you will find Bragg equation there, and you'll find this formula that we also use to determine those questions to do with Bragg equations. So these are the planes, okay? So for BCC, these are the standard reflections that we have, or the planes that form under BCC. Under FCC, these are the planes that will form. Okay, so under FCC, you know A, you solve for A is equal to the square root of 2 multiplied by so on and so on. You find them in the notes. BCC also, there's a formula that we use for A. So those are the ones that you have to work with. You have to memorize them. Okay, different crystal types give different diffraction patterns. Okay. Okay, so this is the next slide. So we look at polymorphism. So 2 or more distinct crystal structures for the same material, okay? So that is where you have a formation of 2 or more distinct crystal structures of the same material. So iron is a good example. So iron forms at a certain temperature, it will form the delta ion, okay, at 1538 BCC. When the temperature as it cools, okay, so this is molten iron just out of production, and it's been released from the furnace at that very high temperature. So at 1538 degrees Celsius, it's BCC, it's known as the delta ion. Coming down to FCC, coming down to a temperature of 1394, it transforms to FCC. It becomes a gamma ion. Then BCC, as it drops down to 912, it goes back to BCC. And that is alpha ion or alpha ferrite, or the ferrite as we usually call it. Titanium also changes also. Okay, it will be HCP, hexagonal packing, and then it will transform to BCC also, or it has these two types. Okay, carbon also has either the diamond or the graphite. Also, they have distinct features. So there's some metals that will have 2 or more distinct crystal structures. Iron, we'll deal with this again when we'll deal with this in future when we probably next week when we look at phase diagrams. So we're going to try and understand with the change in the crystal structure, what advantages come, okay, and what disadvantages come with this transformation. Very interesting to note. Okay, we'll move on. I think this is just densities of material classes. So this is just a table here just to help you understand how density varies with different materials. Okay, so you have the metals, the graphite, ceramics, the semiconductors, the polymers, and the composite fibers. So in terms of density, usually metals, isn't it? Probably the most dense materials we know. So also, it doesn't mean that all metals have the same density, isn't it? Some metals are lighter than others. A non-metal that is quite light and is usually used in industry because of its lightweight is aluminum. We've learned to use aluminum in so many ways. Aluminum foil being a very good example. We know how light aluminum foil is. Okay, that has to do very much with the density of the material itself, being aluminum in this case. And there are also heavy metals, okay, in terms of density. Okay, in terms of density, we have platinum, gold. So platinum there being the most dense, okay, followed by gold, followed by tantalum. And then you have silver there at somewhere around 10, okay, slightly above 10 grams per centimeter cubes. Copper comes in about 9.8. Nickel also finds itself there. Then the steels are a bit lighter than the copper. And then tin and zinc fall below. Titanium also is there. Aluminum and magnesium there being even lighter than aluminum. Then with the graphites, the ceramics, and the semiconductors, as you can see, okay, there are some that level up with certain metals, okay, but there's no graphite or ceramic or semiconductor that is as dense as some of these metals here. Polymers, obviously plastics, isn't it? When you talk about polymers, the most common one is plastics. We cannot expect plastics to be heavier than gold. Just, logically speaking, we deal with a lot of these materials, so we know a lot of them by now. So the PVC, PETs are lighter, okay, in terms of density, they are lighter than graphite, magnesium, aluminum, except silicon there almost levels up. And then we have the glass fibers, wood being the lightest under composites and fibers. Obviously, wood is much lighter. Okay, of course, there are certain types of wood that may be slightly denser than others, but generally wood is a lightweight material. And then there are also other fibers there. Okay, so generally, this is how it is. Metals are heavier than ceramics, which are heavier than polymers. Okay, so why? Because metals have close packing, metallic bonding, often large atomic masses. Ceramics have less dense packing, often lighter materials. Okay, polymers have low density, often amorphous or lighter elements. Composites have what? Intermediate values there. Okay, those who are asking for videos, there's some videos that I've uploaded there on my channel, please. If you want to see some, I'll try and send extra. By the way, you need bundles for these things. I don't send all the time. Okay, so polymers have low packing density. They're often amorphous. Okay, they're lighter elements. Composites have intermediate values. So the composites are where they're here. They have intermediate values generally. When you look at crystals as building blocks, some engineering applications require single crystals, okay? So such as cutting edges for certain equipment, okay? Cutting blades, usually they'll use just one crystal. Why? Because it's just one crystal, it means that it doesn't have boundaries, okay? The grain boundaries, that's where usually the defects come in. And usually when a material fractures, it will usually fracture along those boundaries. So the less the crystals, the less the probability of fracture. So if you just have one single crystal, it's most likely going to be hard and do the job in cutting other materials. So single diamond crystals are used as abrasives, as you can see in this picture here. Properties of crystalline materials often related to crystal structure. So you have quartz fractures more easily along some crystal planes than others. Then you have the turbine blades also. Okay, so in places where you need something that's going to either cut or it's going to encounter so much force or so much pressure, you need to have a material that is as strong as possible. And usually the single crystals are the best for that job. Okay. So this is just about the polycrystals. And this is just a comparison, okay, of the single versus the poly. Poly means many, single versus polycrystals. So the polycrystals, like I said, it's the various grain boundaries. That's where usually the defects will happen. Okay, and that's where the fracture usually happens. It's along these boundaries. Okay, so if you look at anisotropy, you'll find the modulus of elasticity. So we'll look at the modulus of elasticity in our next topic. So you understand this better. It's a bit, now they just look like values, but they'll make much more sense then. So in summary, this is what we've looked at. So our video will be cutting because we've reached the 14-minute limit. So you can just look at those points and we'll start a new topic in the next session, in the next minute.